Hello, my name is Java Haridano, and today we'll be discussing Lab 5 of Physics 2212, Magnetic Braking with Faraday's Law. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet/tube interaction computationally, and compare computational predictions with observed data. Some fundamental concepts covered include Faraday's law, the Biot-Savart law, and Newton's second law. A brief preview of the results shows that our experimental fall time for the magnet is 1.26 seconds, and the computational fall time was slightly faster at 1.16 seconds. Some assumptions we must make are that we treat the bar magnet as a magnetic dipole, air resistance is negligible, and we are using the aluminum foil as a non-ferrous conductive tube. In this experiment, our system is the tube and bar magnet, while our surroundings are everything else. Once again, we treat the bar magnet as a dipole. First, we determine the north side of the bar magnet with a magnetometer app on our phone. Then, holding the tube vertically, we drop the bar magnet down the tube, and we record the time it takes for the magnet to exit. Then, we repeat this experiment 5 times. As you can see, on the left is a table with all of my trials and times. The average time it took was about 1.26 seconds. At the bottom, I've also provided all the measurements of the tube and the magnet that we'll need for the coding portion of this lab. So the following code was used to simulate our experiment. We start by establishing our constants, which includes using the measurements from the slides before for the tube and the magnet, as well as creating our velocity time graph, which is shown in the middle portion. And here I'm just creating the bar magnet and aluminum tube, as well as creating the magnetic field of the bar magnet. And on the bottom right is the function that I'm going to be using to calculate the magnetic flux. Now I'm creating the simulation that is going to be played on the aluminum tube as the magnet travels through it. I'm also calculating the force of gravity on the magnet, as well as the current in the rings, which will affect the velocity in our graph. Finally, here's the completed graph as well as the simulation of the tube. As you can see, the computational fall time for the magnet is about 1.16 seconds. Here we're going to interpret the simulation. So the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions, which color corresponds to clockwise current as viewed from above, and which color counterclockwise. So red corresponds to counterclockwise and blue corresponds to clockwise. And what happens to the dynamic systems when you flip the magnet around? So there would be no physical changes, but the magnetic field would be in the opposite direction. And how does the total time in tube of our real-world system compare to that of our computational system? And how can we make these more accurate? So I think that my experiment was fairly accurate. When I did it myself, I got the result of 1.26, while the simulation it was 1.16, so there's not that much of a difference. But if you do more trials in real life, then that will probably increase the accuracy I got for my experimental portion. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So as you can see in the beginning of the plot from the previous slide, there is a large velocity in the beginning, and this is due to the force of gravity being greater than the magnetic force. And then when we are in the middle, the two forces are even, which causes the slope of the graph to be 0, and which is why it flattens out. And then once the magnet exits the tube, or starts to near the exit of the tube at the very end of the graph, the force of gravity takes over again, and that's why there's this sharp or deep slope in velocity. Now, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The induced current would increase, causing the magnetic force to also increase, which would cause the magnet to fall slower through the tube. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Any holes or slots would disrupt the induced current, which would in turn cause it to decrease, and then this would also cause the magnetic force to decrease, which would make the magnet fall faster through the tube, so these two have opposite effects. And some parting remarks are that while these experiments are usually done with expensive copper tubes, aluminum foil works just fine as it is a non-ferrous but still conductive tube, and aluminum foil also generates no external magnetic field. And once again, as we can see, similar to the likes of Lab 3, bar magnets make good dipoles.